Okay, this video will show you how to calculate the pH of a weak acid. Strong acids are easy in terms of calculating pH because we simply use minus log H plus. We know the concentration of H plus because the acid is fully dissociated, and so pH of a strong acid is quite easy to calculate. When we have a weak acid, the calculation takes a little bit more to do, and then to get the H plus concentration, and then to work out the pH. So let's try an example. We'll try two examples. The first one here is this one that you can see. We've got chloroethanoic acid. You notice you're given the concentration of of the acid, and you're also given the value of Ka, both of which we will need. Right, the first thing to do when you have this kind of question is to write the equation for dissociation. So let's do that then first of all. Okay, right. And we're using a reversible arrows because it's not fully dissociated. So it'll form the anion COO minus and our H plus. Right. We are given the value of the concentration of the acid. So initially we have 0.1 moles per decimeters cubed of the acid before you put it into the water, and we have no dissociation at the very beginning before you put the acid into the water. Once you put the acid into the water, dissociation takes place and an equilibrium is reached. Now at equilibrium we have, let's say, X moles per decimeters cubed of the anion and X moles per decimeters cubed of the H plus. It's a 1-to-1 ratio, and so therefore the values are going to be the same. Now the acid here, at equilibrium, it'll be 0.1 take away X, right? Because this is also in a ratio 1-to-1. Now, because it's a very weak acid, the trick here is that we have to assume that very little will dissociate away. So therefore, the value of X is very tiny, which means that 0.1 take away X is 0.1. We're going to approximate it to 0.1. So we're going to say that that value is 0.1. Right, that's the first thing you do. The next thing you do is write down the expression for Ka. So let's do that next. Okay, Ka. Remember, we have the products on the top, and you multiply the products. So we have your anion and your H plus on the top. Square brackets denote concentration. So concentration of CH2Cl COO minus multiplied by the concentration of H plus. Okay, make sure the line goes all the way underneath, and the reactants on the bottom, which is this. Okay, CH2Cl. Sorry, little mistake. Right, CH2Cl COOH. Okay, there we are. Right, now we need to put in the value. So we put X for these two. We put 0.1 for the acid, and we know the value of Ka, which is this here. Okay, so let's do that then. Remember, our purpose is to find the concentration of X, concentration of H plus, which is X. So let's put the values in, and then we'll rearrange to get H plus. So Ka, 1.3 times 10 to the minus 3 equals x squared over 0.1, right? From which, if you rearrange that, you'll have x squared equals 1.3 times 10 to the minus 4. Okay, just a little bit of maths there. And you can now find the x by square rooting this value. So x will be, if I square root that value, 1.3 times 10 to the minus 4, I will get 0.0114. So 0.0114 is our value of x, which is the concentration of H+. And once you have the concentration of H+, you now can work out your pH. So x equals 0.0114, and the units are moles per decimeters cubed, and so pH equals minus log to the base 10 of 0.0114, right, equals, and that will give you a value of 1.94. Okay, now in the question it may ask you to give your answer to 2 decimal places or 1 decimal place or significant figures, so be aware of that. That could be worth a mark as well. So this is to 2 decimal places, and remember there are no units for pH. Okay, right. Next we'll go on to do another calculation in a second. Right, just pause. Okay, so this is another example, but this time slightly more difficult because you have a diprotic acid. So you're going to get 2 H+ ions in solution, right? So we'll follow the same procedure as before. Let's write the dissociation equation first, right? Right, so I've just generalized it as a H2A representing the dicarboxylic acid. So H2A in solution, it'll dissociate to A, 2 minus, and 2 H+ ions, okay, in solution. And remember, it's a weak acid, so it's not going to dissociate much. Right, initially, we know the concentration of the acid is 0.1, and we have nothing of this and nothing of that at the very, very start. Right, at equilibrium, we have x moles per decimeters cubed of the anion, and because it's 1 to 2, you will have 2x moles per decimeters cubed of the H+. Right, 1 to 2. Right, and this will now reduce to 0.1 take away x. It's a 1 to 1. It's a 1 to 1 ratio, so 0.1 take away x. Okay, right, and remember that this will approximate to 0.1. There we are. Okay, so that's an assumption we have to make, but it's very, very close to 0.1, so it's a good assumption to make, and it makes the calculation obviously easier. Right, that's the first thing. The second thing we do is to again write down the expression Ka. So let's do that. Ka equals products on top, A2 concentration of A2 minus times the concentration of H+, and because we have 2, then we have to square that concentration value. Okay, and on the bottom we have our reactant, which is H2A, concentration of H2A. Right, we know the value of Ka, we're given that, there it is. And we know the value of H2A, our acid, and these two are x and 2x. So let's put the values in. We've got 1.7 times 10 to the minus 3 equals, that is x times that value for H plus is there, 2x, and it's squared. So the value of H is 2x, and we're going to square all that. There we are. Divided by H2A, which is 0.1. 0.1. Okay. Let's rearrange this to get x on one side. So it'll be 1.7 times 10 to the minus 3 times 0.1 equals x times 2x squared. 2x squared is 4x squared, and times x, 4x cubed. Right, there we are. Now we need to get x by itself, so let's just do that. 1.7 10 to the minus 3. Right, 1.7 times 10 to the minus 3 times 0.1 equals 4x cubed. And if I want x, 1.7 times 10 to the minus 4, that times that is 10 to the minus 4, divided by 4 equals x cubed. And then you want the cube root of this to find x. Right, so cube root of that, and that is 1.7 times 10 to the minus 4 divided by 4 to find the value of x. I'll just pause that. Okay, so if I do that, I will get the cube root of 4.25 times 10 to the minus 5 and that comes to 0.0349 moles per decimeters cubed. Okay, and then you work out the pH at the end, minus log this value, 349, and that'll give us your pH. That comes to 1.45 as your final pH value. Right, so just looking through that one more time. Okay, what you do is a diprotic acid. You may get this on an exam paper. Normally it's a monoprotic, but if you get a diprotic, this is what you would do. Write the expression, the equation, dissociating like so. You get 2 H pluses, and then you write down what you have at equilibrium. Right, x, and that's 2x. Ratio is 1 to 2, so x to 2x. Expression for Ka, products on top, A2 minus times H plus squared, because you got the 2 there, it's not there. And then the reactants on the bottom. You put in your values, you're given Ka, 1.7 times 10 to the minus 3 in this case, x times 2x squared, 2x all squared, over 0.1, and it gives you that. And it's all maths, as you can see from here. So following it through, you find x. Once you've got x, you now use a pH equation to find your pH value. There we go. Okay, that's it.